Hello, welcome to Exponential Functions. This is 5.4. We're doing exponential functions, differentiation, and integration. Now, it does help that we just talked about inverse functions because the exponential function is the inverse of something. Anyone know what? What is it the inverse of? Oh, you're right, the natural logarithmic function. F of x, which is natural log of x, its inverse is called the natural exponential function, is denoted by f inverse of x is e to the x. So e to the x is the inverse of natural log of x. You probably kind of knew that because I know I teach that in my pre-calculus. So I'm hoping everyone knows that. No big surprises. So y equals e to the x if and only if x equals natural log of y. Remember, natural log is the log base e. The natural log of e to the x is x, and e to the natural log of x is x. They cancel each other out. Remember we talked about f of f inverse of x is x. We're seeing that here. Okay, so for example 1, it says solving exponential equations. 6 to the x equals 72. Now if we took the natural log of 6 to the x and the natural log of 72, now it would be nice to take log base 6, but unless you have like a TI, Inspire, CAS, you can only do log base e, which is natural log, or the common log. So by taking the natural log of both sides, this x will come out front. So it'll be x natural log of 6 equals natural log of 72. Dividing both sides by the natural log of 6, x would equal 2.3869. If you check that in your calculator, if you do 6 to the 2.3869, this is just rounding off to 4 places, you would end up with 72.006. So it's close. I mean, there's some round-off error in there. Solve the logarithmic equation. Natural log of x minus 3 equals 2. So to undo a natural log, say e to the natural log of x minus 3 equals e to the 2. And e to the natural log that cancels, and this is probably not exactly the right way to write this. We'd say x minus 3 equals e to the 2. I mean, this is correct. Doing that canceling may not be exactly correct. Then we add 3 to both sides, and x equals 3 plus e squared. And there you go. That's the exact value. If you want a decimal approximation, it's going to be 10.3891. Okay, so Theorem 5.10, operations of the exponential functions. This is a review. Let a and b be any real numbers. E to the a times e to the b is e to the a plus b. And e to the a divided by e to the b is e to the a minus b. Too high up. Properties of the natural exponential function. Now the domain, you can plug anything in from negative infinity to infinity, but it's only going to produce positives from 0 to infinity. The function f of x equals e to the x is continuous and increasing and 1 to 1 on its entire domain. And the graph of f of x equals e to the x is concave upward on its entire domain. The limit as x goes to negative infinity of e to the x is 0, and the limit as x goes to infinity of e to the x is infinity. Now here's a really cool thing. You're going to like this. You're going to be so happy about this through this class and the rest of this class anyway. And then when you go on to Calculus 2, which you should all go on to Calculus 2. The derivative with respect to x of e to the x is, drum roll, e to the x. It's its own derivative. That's really cool. That's a neat thing. And if you add some other function in there, the derivative with respect to x of e to the u is going to be e to the u du dx. That's just the chain rule. But that's a really neat thing. The derivative is itself. Let's look at example 3. Differentiating exponential functions, find the derivative. So our dy dx It's going to be this derivative of this thing here, e to the negative x squared times the derivative with respect to x of negative x squared. So dy dx is e to the negative x squared times negative 2x. So dy dx is negative 2x e to the negative x squared. Over here, g prime of t is going to be e to the, well, we have something cubed here, so bring the 3 out front, e to the negative t plus e to the t to the 2 power, then times the derivative of what's inside. What's the derivative of e to the negative t? That's e to the negative t times dt of negative t plus this e to the t. So g prime of t is going to be 3 e to the negative t plus e to the t squared times negative t e to the negative t plus, no, so that should be negative 1, plus e to the t. So g prime of t is 3 e to the negative t plus e to the t squared times negative e to the negative t plus e to the t. Example 4. It says find all relative extrema. I'm going to have to move this up, so if you need to erase it, you can. I'm going to erase it. If you need to pause, please do so. Find all relative extrema and the points of inflection, if any exist, of the function. Use a graphing utility to graph the function and confirm your results. Do that. I read it to you already. So we're going to look for the derivative here first, and then the second derivative. So you can look at this as f of x equals 1/2 times e to the x minus e to the negative x. So f prime of x is going to be 1/2 times e to the x minus e to the negative x times the derivative with respect to x of negative x. That's going to be 1/2 e to the x minus e to the negative x times negative 1. So we get 1/2 e to the negative x plus e to the negative x is our derivative. Now, e to the x plus e to the negative x, that first derivative over 2, that's going to be positive because e to the x produces positives, e to the negative x produces positive. They're both they're being added here. Those are always positives. So that means it's increasing. So there are no relative extrema. Now for the second derivative, this might look familiar to you. Again, think of this 1/2. Think back to this to view it. That's 1/2 times the derivative of e to the x is e to the x plus the derivative of e to the negative x is e to the negative x times the derivative with respect to x of negative x. It's 1/2 times e to the x plus e to the negative x times negative 1, which is 1/2 times e to the x minus e to the negative x. That's what we started with. So if we take 1/2 of e to the x minus e to the negative x, set it equal to 0. I can multiply both sides by 2. Then we have e to the x minus e to the negative x equals 0. Then if I add that to the other side, e to the x equals 1 over e to the x. Because e to the negative x is 1 over e to the x. Multiply both sides by e to the x. I have e to the same base, so we add the powers. It's e to the 2x equals 1. natural log of e to the 2x equals natural log of 1. So 2x equals 0. X must be 0. The only place that we are finding any inflection point possibility is at 0. We see that here. If x is 0, e to the 0 is 1, minus e to the negative 0, that's still 1. 1 minus 1 is 0. So there's our inflection points. And I think you can also see, 0 being that critical value. Say e to the x minus e to the negative x over 2. If you put something negative in here, like, I don't know, let's do a test value. Let's go negative 1, let's go 1. Okay, so we're looking here at e to the negative 1 minus e to the negative of negative 1 over 2. That's going to be 1 over e minus e over 2. That's going to be negative. So we're concave down there. If you plug in the positive 1, that's going to be e to the 1 minus e to the negative 1 over 2. That's e minus 1 over e over 2. And that's positive. That means we're concave up here. And that confirms that we have a point of inflection. We change concavity from concave down to concave up. Okay, I'm going to go on to the next page. Example 5. Several parts to this one. Several graphs for it anyway. So let's find all relative extrema and points of inflection, if any exist, of the function. Use graphing utility to graph the function and confirm your results. Okay, so g of x equals 1 over the square root of 2 pi e to the negative of x minus 3 quantity squared over 2. Now this is a version of the normal curve. So our g prime of x is 1 over the square root of 2 pi times e to the negative of x minus 3 squared over 2 times the derivative with respect to x of negative of x minus 3 squared over 2. So our g prime of x is going to be 1 over the square root of 2 pi times e to the negative of x minus 3 squared over 2 times this derivative is going to be this negative 1/2 times x minus 3, the 1, then times 2 from the power. The derivative of what's inside is just 1, so we don't have to worry about that. But this 2 divides out with that 2. And we end up with negative 1 over the square root of 2 pi times e to the negative of x minus 3 squared over 2 times x minus 3. So where is, this part up here, this e to the negative x minus 3 squared over 2, that's never going to be 0. That's always positive. So if we want to find zeros, look at negative 1 over the square root of 2 pi times x minus 3. When's that 0? Well, multiply both sides by negative 1 over the square root of 2 pi, and you have x minus 3 is 0. So x minus 3 is 0. X equals 3 is the only critical number we're going to have. And we see that here. That's a max. Now let's do our second derivative. Using this here, we're going to have to use a product rule because we have two functions with x in it. So we have negative 1 over the square root of 2 pi times e to the negative of x minus 3 squared over 2 times the derivative with respect to x of x minus 3 plus negative 1 over the square root of 2 pi times the derivative with respect to x of e to the negative x minus 3 squared over 2, and then we're going to multiply by x minus 3. And the key here is we already found this. That's our first derivative. That's this answer up here. So our second derivative is going to be negative 1 over the square root of 2 pi times e to the negative x minus 3, negatives on the outside, squared over 2 times this derivative of just 1 plus negative 1 over the square root of 2 pi times e to the negative of x minus 3 squared over 2 times and then this derivative here, we have this negative. I think we dropped our negative by mistake. Oh, we brought the negative out front. That's where it was. Okay. So we have this negative x minus 3 then times that x minus 3, which gives us g double prime of x. And notice here we have negative 1 over the square root of 2 pi e to the negative x minus 3 squared over 2. We have it there. We have it again right here. So I can factor that out and have negative 1 over the square root of 2 pi times e to the negative of x minus 3 squared over 2 times, factoring out 1 plus, we have this negative of x minus 3 squared. So this first part's always, well, it's never going to be 0. The second part can be 0, so we do 1 minus x minus 3 squared equals 0. It means 1 equals x, I'm going to FOIL that out, x squared plus 6, no, minus 6x plus 9. If I subtract 1 from both sides, we have 0 equals x squared minus 6x plus 8. So 0 equals x minus 2 times x minus 4. So x equals 2 and 4. Those are the inflection points. Let me scroll this up for a second here. So here's our 3, x equals 3 right there. I should say, here's x equals 3. And then we have x equals 2 in this picture right there. X equals 2 and x equals 4. Those are inflection points. Inflection and inflection. So I had the calculator find the inflection points as well. That verifies them. Okay. I'm going to move on. A lot of work we just did there. It says Theorem 512, integration rules for exponential functions, although it's probably in the bright spot of the board. Integration. Now, if the derivative of an exponential base e is going to be e times whatever the derivative of the power is, integration of e to the x is just e to the x plus c. And the integral of e to the u du is going to be e to the u plus c. That's cool. That's really helpful. That's nice. So you evaluate the integral of e to the negative x to the fourth times negative 4x cubed. Just to check, I mean, if my u is negative x to the fourth, my derivative of that is negative 4x cubed dx. And we have that. So this part is the du, and for that being the u. So this is going to be the e to the negative x to the fourth plus some constant c. That's it. Voila. Kind of cool. Example 7. In this case, we have e to the negative x over 1 plus e to the negative x. I would recommend the denominator is a little more complicated, so if you said u equals that denominator, its derivative is going to be derivative of a 1 is 0, derivative of e to the x, e to the negative x is going to be negative e to the negative x dx. We have positive e to the negative x, so we could say negative du equals e to the negative x dx. And that makes this negative the integral of 1 over u du. That's my u. And this becomes the negative natural log of the absolute value of u plus c, which is negative natural log of 1 plus e to the negative x plus c. I can drop the absolute value because 1 plus e to the negative x is always positive. Okay, I'm going to go on to the last example. Evaluate the definite integral. Use a graphing utility to verify your result. We have the integral from 0 to 1 of e to the negative 2x dx. If I say u is negative 2x, my du is negative 2 dx. I don't have that, negative 2 dx. So here's one way. If we don't want to change our limits of integration, we could do it like this. Negative 1/2 times negative 2 times, so this is just 1, times the integral from 0 to 1 of e to the negative 2x dx. So I'm kind of setting this up. This becomes negative 1/2 integral of e to the negative 2x times negative 2 dx from 0 to 1. So now we have the components here for this u and du, so to speak. This is negative 1/2, that's not going to go away, times e to the negative 2x from 0 to 1. That's negative 1/2 e to the negative 2 times 1 or minus e to the negative 2 times 0. So it's negative 1/2 times 1 over e squared minus e to the 0 is just 1. So if we distribute the negative 1/2 through, it's going to be negative 1 over 2e squared plus 1/2. And that should be approximately 0.432332. In the notes, I did this. I did the u substitution and changed limits of integration. It's really important. I fall back to that all the time. Probably a teacher in me, I want people to be able to do this method as well, so you can see either. Okay, and that'll do it for this one. Here's the graph of that. Do it for this section. So, send me your questions. Thank you.